Welcome everyone to TalentSHIFT and TryEngineering Learning Workshop, making of a microchip. My name is Phil Beloka, part of the TalentSHIFT team. We all hope you are ready to roll up your sleeves today for a hands-on session where you'll build simple circuits and walk through a chip making exercise that you can bring to your classrooms. On the next slide, I'm going to go over some logistics for today. Closed captioning is provided. You'll want to click it down at the bottom of your screen. Turn your camera on. We want to see everyone. We'll all be working diligently on our semiconductors, and we want to see your faces and your smiles. Please mute yourself when you're not speaking so that we don't have a lot of background noise. If you experience technical difficulties, just send a message to the host in chat and we'll try to help you as much as we can. If you have a question, use the Q&A function. It's located at the bottom of your screen. We will have a Q&A section of this webinar, so we'll be able to answer as many as we can get to. And then the recording and other materials will be provided after the event. Great. On the next slide, I'm going to go over the agenda. I'm going to talk a little bit about what TalentSHIFT is for those that don't know. I'll introduce the IEEE and TryEngineering team, and they'll give us a background of who they are and what they're about to do. As far as the presentation and the activities we'll be doing, we'll go through the activities, and then we will talk about some key takeaways after the activity, and then we'll go through a brief Q&A section, and then any further announcements that we have at the end. Okay, so I'm going to talk a little bit about TalentSHIFT. It's an advanced manufacturing collaborative. It's a growing national community of practice for educators, industry leaders, workforce development partners. Basically, it is a collaborative of people who are working together to build stronger connections between education and industry. We all know that there is a lot of times a disconnect between what industry is doing and what education is teaching. So we want to bridge that gap and prepare a skilled, future-ready manufacturing workforce. The collaborative is working together to build those strong connections, and some of the benefits of the collaborative. Our members are able to network with their peers nationwide, share best practices, their success stories and lessons learned. We can collaborate together to overcome barriers and co-create solutions. You'll have access to curated resources and tools in our online hub that you can use for your everyday work. And then you can participate in events just like this learning workshop. We also have discussions and other learning opportunities. We have virtual meetups for people to join us nationwide. So a lot of stuff that you can do with this collaborative. And we've got a link in the chat if you're interested in checking it out. We hope you join the collaborative now and in the future. So with that, I'm going to turn it over to our IEEE TryEngineering team, who are going to introduce themselves and then walk us through the activity.
Thank you, Phil, and thank you for the opportunity to be a part of this event today. My name is Deborah Gulick. I am the Director of Student and Academic Programs for Educational Activities here at IEEE. IEEE is the world's largest technical professional association benefiting humanity through technology. Our goals are to not only provide our professional members with a network to learn from each other. In fact, we are one of the world's largest publishers of technical information and research, but also to inspire the workforce of the future. In order to inspire the workforce of the future, most of our lessons, videos, and resources live in something called TryEngineering, which is a website. I'll put the link in the chat in just a second, which is coordinated by our Senior STEM Outreach Manager, Donna Schultz. She brought together a CEO of a chip integrated circuit company, a chip designer from California, and volunteers from across the organization to build, test, and design these lessons. And we hope you enjoy it today.
Thank you so much, Debbie. Appreciate it. I'm so excited to be here with you today. I'm just going to share my screen. Everybody see my screen? Yes?
Looks great.
Good. I see a lot of nods. Great. Thank you so much. Well, welcome everyone. We are going to be diving into the fascinating world of semiconductors and microchips. Let's explore how they're made, why they matter, and how we can bring this knowledge to our students. So for today's session agenda, the activity agenda specifically, we're going to introduce the activity, we're going to feature a design challenge, and then we're going to talk about all the resources that you can use around those challenges. And then we're going to talk about some special opportunities for educator sessions, and we'll close out with some question and answers. Semiconductors, here we go. When you hear the word semiconductor, what pops into your mind? Let's take a moment to surface those images because they're important for understanding how students might think about this topic as well. So if you can for me, I'd love to see some answers in the chat. I see metal, connections, great. Thank you, Quinn. Connectors, great. Thanks, Bobby. Microchips, flat squares, operations, high tech, electricity, chips, power. Yes, integrated circuits, flow, silicone. Wonderful. That's great. That's great. One final one here, silicone with electrical conductivity. You guys are all on it. That's great. So all that you're saying is absolutely true. Those are all part of the story that of semiconductors, right? Here are some examples, some images that may have come up. I heard the word chip in there, integrated circuits, silicone, electricity. Here in this image, you can see a shiny wafer. I didn't see the word wafer yet. Microchip. What about engineers in bunny suits? Maybe mining silicone. We got that one over there. That's great. So again, all of these are actually visuals that help us connect these abstract concepts to real-world objects. And they're all part of the story of semiconductors. However, semiconductor is actually a material. So if you were defining that word, semiconductor, it wouldn't be a microchip. It wouldn't be, right, power, integrated circuits. It is a material. It's a special material called a metalloid. And silicone, right, is probably the most popular, but there's gallium and others that are also semiconductor materials. And what that means is that they can be both a conductor and an insulator of electricity. And it's just like the name says, you guys, semiconductor. It sometimes conducts and it sometimes doesn't. So semiconductors are so cool because they have just the right electrical properties to be engineered into those microchips that you guys kept imagining, right? When I asked, silicone is mined. You can see here in the picture, it's mined and then melted and then pulled into an ingot, which is this long cylinder that you can see on the far right with the pointed tip. And then that ingot is sliced into those thin wafers. All right, so now that we know what semiconductor is, what are these materials used to make? Take a minute and let's pop that into the chat. I think we already know. We're kind of getting there. Yes, great, Quinn. Great. I'm seeing applications. I see phones and chips. Fantastic. All right. Whoop, did I go? Yeah. So semiconductors, TVs, great. Keep the applications coming. That's awesome. So semiconductors are needed to make what's called a microchip. And that word chip and semi-chip and semiconductor chips and semi are all used to define the word microchip. And that is an integrated circuit. I heard that over somebody popped integrated circuit early on. That's an integrated circuit is etched on wafers. And pretty much every modern electronics that you guys are popping in the chat, right, have to have a microchip. So all of our electronics today rely on semiconductors. Semiconductors are the foundations of microchips. Engineers take these materials and they process them in layers. They create circuits and that can store amazing information, perform calculations, and control systems. So microchips are really the brains inside our technology. Yeah, oh, I'm seeing transistors in there. You're way ahead of us. That's great. So you already kind of did this, right? But now that we know that semiconductors are needed to make microchips, where do we find all the microchips? We've been alluding to them, but let's pop in even more applications, even more technologies where microchips might be. Think of the ones that maybe others might not think of. Think of those interesting ones that you have in your home or at school. And pop those in the chat for me. Great. Ooh, yes. Ooh, healthcare tools and televisions, phones, cars. Beautiful. Yep. All right, here's some pictures. Oh, keep going, keep going. I love it. Yep. Solar cells, digital watches, everything, right? Microchips are literally everywhere. It's crazy. And if you have in your pocket, in your home, in your car, in your school, and even everyday objects, right? Like the washing machine, your toaster, a camera, your computer, and obviously big things like airplanes and fighter jets and your car, right? Thermostats, everything, right? Everything, just about everything today. Your coffee maker, right? Has a microchip. So understanding microchips helps students to see that engineering, helps students to see the engineering behind the world all around them. It's amazing how important microchips are, and there go semiconductors, right? All right, thank you for participating in the chat. I really appreciate it. We'll keep that rolling throughout. What we're going to do next, though, is we're going to watch a video that summarizes all that we just talked about and hopefully further clarify what a semiconductor is.
I'll get you right up in just a second.
No worries. Perfect. Thank you.
Semiconductors make your life smarter. They are in your phones, your houses, your cars, your computer. They are everywhere, doing big things. It is hard to imagine a technological advancement more important than semiconductors. Before we go any further, let's first make sure we understand what a semiconductor is.
Before we go any further, let's talk about what a semiconductor is, and let's start with something that you have experience with. So if we think about two types of cups and we want to put a hot drink in it, say like cocoa, into these two cups, our experience with them is going to be fairly different. If a really, really hot liquid is in the metal cup, when we touch it, we're going to feel all that heat. Okay, this cup lets the heat pass through. We would call this a conductor. So over here, if we pour the hot liquid into this foam cup, when we feel it, might feel a little bit of warmth, but mostly it blocks most of that heat, and we call that an insulator. So we also have that in electricity. So you guys experience electricity in a lot of different ways in your life, but think about your charging cables for your devices. On the outside, there's plastic, and that protects us from the electricity, blocks the electricity. It's an insulator. Inside the wire, there's metal. These are copper wires. They conduct electricity, allows electricity to get from your wall to charging your device. So in electricity, we can also do both conductors and insulators. But what's nice is also in electricity, we can create something that's in between these two cups. Think about if we wanted a cup that could be both a conductor and an insulator. So we want to pour our hot liquid in, it's too hot to drink. So we could say, cup, I want you to be a conductor. I want you to let the heat pass through. But then when your drink gets to just the right temperature, you can switch it and say, now I want you to be an insulator and keep that heat in so it stays warm so you can finish it. That is what we call a semiconductor. It can act like a conductor in some ways and an insulator in other ways, and really anywhere in between. We have the ability to control how much of a conductor it is and how much of an insulator it is, and that's what opens up the world of electronics to what it is today.
Silicon semiconductors are the most common, and to make these, we begin with sand. After the sand is mined, it is heated until it crystallizes. The crystal is then melted down and formed into an ingot, which looks like this. The ingot is then sliced into thin pieces called wafers.
And so right here, I'm holding a silicon wafer. And so from this wafer of silicon, this is where we can start playing with the semiconductor.
A wafer must go through several important processes before it is ready to become the foundation of a semiconductor. First, a thorough cleaning takes place. Using chemicals and gases, impurities that remain on the wafer are removed. Each semiconductor has its own design, which lays out the electrical circuitry. Designers take great care while creating these roadmaps for the electric currents. Because we are going to be adding circuit patterns to the wafer, we need to know where to put them. Photolithography is used to help make this happen. A computer-generated design is created and is drawn on the wafer. The next important step is called deposition and interconnection. This involves building many thin layers on the wafer and adding molecular elements so electricity can be transmitted. This process is repeated over and over so that layers are formed and connected to create the circuit. Etching follows and is used to carefully remove all unnecessary elements. Because so many high-tech processes are involved in the production of a semiconductor, testing is a critical part of the workflow and is scheduled throughout the entire process. Today, silicon wafers are the most commonly used in the manufacturing of semiconductors. But as the demand for faster, more reliable semiconductors, which can work in extreme conditions, increases, scientists and researchers are constantly looking for new materials that could result in better performance. Meet Dr. Morgan Ware, who spends his days researching and testing different materials which might work better than silicon.
There's lots of different research going on for lots of different directions, but one of the things we look at is ways of making those devices not necessarily smaller, but the same size, maybe larger, but faster because of the properties.
Dr. Ware takes different materials, crystallizes them, and then tests their performance in a semiconductor.
All these different crystals are semiconductors that will have different properties that allow us to make different useful devices and push the technology farther, make everybody happier, allow us to look in different places that we've never looked before. And so that's why we look at semiconductors, because they allow the technology to go farther.
Donna, you're muted.
Unmute. Let me share my screen again. Hold on. There we go. Share. You guys see it?
Looks great.
Oh, great, great, thank you. So I hope that video clarified any confusion you may have had about semiconductors. I would love to get your feedback in the chat on, what did you think? Did it clarify? Did it raise any further questions for you? Great, thank you. Great feedback. Excellent. All right. I am so excited to dive into the design challenge with you. Now we get to roll up our sleeves and get started on actually building a model, a microchip model. So we're gonna put the direct link actually of this lesson into the chat. Thank you so much. And what we're gonna do is we're actually gonna take on the role of semiconductor engineers. Imagine that you're working in a foundry or a lab. That's that clean lab where you make microchips. And we're going to explore how a chip is made by making a model of a chip using Play-Doh. We're going to need to embark on 3 different phases that will ultimately lead to the microchip model. The first one is we're going to learn a little bit about basic circuits, and that challenge is an electric dough challenge. Then we're going to spend time designing a mask for the microchip model, and that which you'll learn about. And then the last piece is we'll assemble it all and then we'll test. All right, so let's get going. First things first, I want to show you a little, we'll sort of pan across our materials. Now, if you have materials, please get them out because we're going to be using them. But if you don't have the materials, do not worry. What I recommend is you grab a piece of paper and a pencil, and you can participate by sketching your ideas and your solutions. Let's take a quick peek at the materials. They're not that bad. It's Play-Doh, it's clay, some LEDs, a battery pack, scissors, tweezers. I'll play it one more time. Tweezers, see pencil, sandwich. In your battery pack. All right. So, but before we jump into this task, we need to understand, before we jump into actually the task of making the model, we need to understand this very basic idea of a basic circuit and electronics and the difference between those conductors and insulators that are so incredibly important to semiconductors. So today we're going to be exploring building a simple circuit using Play-Doh. And modeling clay eventually, but Play-Doh acts as the conductor, and that means electricity can flow through it easily. And modeling clay will represent the insulator, which means electricity cannot pass through it. And we'll use both of these materials to shape and test our circuits. So I'm going to show you, we're going to get started together. So first thing first, I want you to get out your Play-Doh. We're going to open it, and we're going to break it into 2 chunks. You can roll them into beautiful little circles or leave them as chunks. Either is fine. We're going to roll them into nice circles, nice round balls. I'm going to put them fairly close together because what you're going to do next is you're going to take your LED. Yeah, fairly close, but notice not touching. You're going to take your LED and you're going to stick one leg into one circle and the other leg into the other ball of dough. Great. Now you're going to take your battery pack and put one wire into one side of the dough and one wire into the other side. And, oh, it should be lighting up, but it is not. So now it does light up. I'm going to stop right there. And I want to just mention one thing. If the LED isn't lighting up for you, you want to flip the battery pack wires like you see here. And this happens due to polarity. And that's the direction required for the current to flow through the circuit. Both the LED and the battery pack need to work together. An LED, which is a light emitting diode, is it's one-way street for electricity. The current must flow from its positive terminal, which is called an anode. That's the long leg, or its negative terminal, which is the cathode or the shorter leg. The battery pack also has a fixed polarity, a positive and a negative. So if the circuit doesn't work, reversing the battery pack wires ensures the positive side of the battery connects to the LED's anode, allowing the current to flow and the LED to light up. So I want to just point that out. Make sure we talked a little bit about polarity. Let's continue. Great. Now, what's happening now? So what we did is if you saw, we pushed it together, the two Play-Doh pieces together, and it caused something called a short. And what that is that's when the wires they're not supposed to touch are touching. Basically, they're overlapping in some way, shorting the circuit, meaning the current can't flow through because it's confused. So we don't want the Play-Doh to touch. Those two LED legs cannot be connected. So let's see what you can do to resolve that. What we're doing is, remember, we're taking the clay, which is the insulator. So we're going to take a piece of clay, and we're going to use the clay to our advantage. We're going to put it in between the two LED legs, between the two Play-Doh pieces, with the LED straddling that insulating dough, allowing us to put the two Play-Doh pieces closer together, which will help later on when you're doing this next piece. So notice we're going to try and add a couple more LEDs. Yep. So we got two, and then we're going to try and do a third one. Now that is a parallel circuit. I would not normally tell you, but we're crunched in time. So that's a parallel circuit. And I'm going to ask you next to explore this idea of insulators and conductors using the Play-Doh and the clay to make both parallel and series creations like sculptures. Let me show you what I mean. I'm going to go to the next slide. Here is an example. We reference the short. We show you the two pieces of circular Play-Doh. And then on the right, you can see an example of series and parallel circuits. So what I'd love for you to do is to go ahead and start experimenting. Try making fun shapes and creative designs by keeping one important rule in mind. Don't short your circuit. Make sure there's always a piece of insulating clay between the two LED legs so that the current can flow through. So I'll give a few minutes and we'll see how you all do. Have fun. I will say, if anybody is willing, if anybody did have their materials, or if you didn't, I would love to see a sketch of your ideas of your series or parallel circuit. So I'm going to be looking now on your video to see if anybody's holding anything up. I would love to see any solutions you may have. I see people are working. This is good. Give you a few more minutes. While we're letting everybody work for another minute or two, I just want to mention that, and I think all of you probably know this, that failure, and we call it often productive failure, is very much part of all of the engineering design challenges that we have in the TryEngineering suite of challenges. So productive failure is critical. It's part of the engineering design process. So engineers fail and they try again and again and again. They iterate till they get to the best solution. So one thing that we always work to make sure we encourage our kids, that failure is normal. Like, you want to fail and try again because that's how you get the best solution. So wanted to just note that while we're all working. Good question, Richard. You can, if you short, you can cause a fire. Yep, we've experienced that, haven't we, Debbie? So it can get hot and burn you. So that's important. You don't. It's a safety, tip that you want to make sure kids know for sure. Good point. Excellent. Anybody have any that they want to show us? I'm going to keep scrolling through. That's all right. Maybe by the end, we'll see where you're. Great. Thanks, Richard. All right. All right, let's move on. Because that's just the precursor to the big challenge, which is actually making of the microchip. So now we're going to, I'm going to say welcome to the fab. For this activity, we want you to imagine that you are a semiconductor engineer working inside a foundry, or fab for short. And the fab, as you know, is that special kind of manufacturing facility where these microchips are made. And these spaces are incredibly clean, precise, and that's where these tiny circuits are made inside. That's where the microchips are made, and it is so important that the room is clean. Now we don't have a clean room today, but we're imagining that we have our bunny suits on. So let's get started. All right, your first job is to explore how a microchip is made in this lab, and we're going to be building our own model. So think of this as a hands-on simulation of the fabrication steps of making the microchip. And as you shape and layer and pattern your Play-Doh and clay, you'll get a feel of how engineers create these structures, eventually becoming working microchips. So here we go. We're going to step into your role as a fab engineer, roll up our sleeves, and we're going to get started making our microchips models. All right, here we go. I'm going to press my play. Oh, can you guys see? Here we go. There we go. All right, so first things first, get more Play-Doh. You can pick a different color. And you're going to create that very first layer, which is going to be our silicone wafer. So we've got to start with the silicone wafer. We're going to make this into a kind of like a hamburger patty that's about 3 to 4 inches in diameter. And this very first layer is our wafer. Now, the next thing that you're going to do is you're going to grab that sandwich bag. And I want to make note that you want these sandwich bags to be thin, not the really expensive kind, but the cheaper sandwich bags that are thinner. And you're going to cut a plastic circle, and we're going to layer that on top of your wafer. And this step is representing the cleaning and polishing step of the process, the cleaning and polishing of the wafer. So here we go. It will actually look polished when we flatten it out. All right, so now we've got our wafer, we've cleaned and polished it, and the next step is we're going to add another layer. This layer represents the photoresistant coating. It's a light-sensitive material. And it's going to be on this layer that we model the integrated circuit. But let's get this layer on now. Photoresistant coating, a light-sensitive material, getting ready for the integrated circuit. All right. Great. So we've got the wafer, we've got the cleaning and polishing of the wafer, and then we've got the photoresistant material. All right, we're going to pause. We're actually going to take off our hat of the semiconductor engineer. We're going to put on a hat of an integrated circuit designer. So let's move over here. Hold on, let me get to the next. So we're going to take on this role of the integrated circuit designer. They are like a city planner for a microchip. Their job is to arrange all the electrical parts. And we've already mentioned transistors, but what about resistors and all sorts of electronic parts to create the circuit blueprint, which is essential for all of the modern electronics that we've talked about. So before we get into this activity, I want to talk to you about something very cool and fun. It's called chip art, also known as silicone art or chip graffiti. I want to point your eye to that image down the bottom that says chip art, right? So I'm going to talk to you about that in a second, but you can be looking at that. This chip art, these are microscopic doodles or sketches that engineers secretly hide on a microchip during manufacturing. And the image that I have there for you is one of the most famous examples of chip art. It's this tiny, tiny image of Waldo from, remember Where's Waldo? And we're going to come back to this. So the chip art's going to be part of this challenge, but I want to just, kind of note it for you. I think it's so cool. And so this activity of creating the circuit design is turned into what's called the mask. All right. And so the circuit design is stamped on the mask and on the mask material. Remember that photoresistant material that we just laid down on the wafer? The circuit design comes next. And so this mask is critical to laying down the integrated circuit. And so the mask material, and then you lay down your mask and then cut out, lay down the mask material, and then cut out, leaving the mask and the stencil of the negative of the circuit. Light then is transferred to create the imprint of the circuit onto the wafer, exposing the parts that we can remove, all right? So this task for us is to create our mask. I'm so excited. This is my favorite task. It's one where you get that art element that will engage many of your kids. So your challenge is to create your own version of chip art with 6 to 8 chips, making a recognizable shape or object like the ones you see here. You see I have the sun. Does that look like the sun, everybody? Then I have a city skyline, and then I have mountains. You could also consider doing your first initial, your last initial, or a number. But I want to point your attention to the very top image that says 6 chips. So each of those little 6 chips, they are little rectangles with 2 hole punches. That represents one microchip. And so you're going to need to make those. That's a critical piece. You want to make those because you're going to be able to orient those onto your mask. And so we're gonna step through this in a minute, but I want to just point that out to you because it's really important that you understand that these are microchips that we're going to be organizing into a shape, or we might even challenge ourselves to put as many microchips onto the mask. So let me go ahead and let's do this, and I'll kind of talk you through all the steps if it's not clear yet. Hold on, let's get to it. Here we go. So first things first, we've got to create the basic shape for the mask, and the mask, like everything else, is circular. So we recommend, if you want it to look like a perfect circle, to use a cup. Then you cut this out. This is also going to be about the same size as your wafer, which is 3 to 4 inches in diameter. Again, each chip will be modeled by a set of 2 hole punches. You don't want those 2 hole punches to be too close because you'll short your circuit, all right? It's very helpful to make them, as I said, so that you can physically test the placement of them on the wafer like we just did. And so once you test and you get the shape, like we're going to do the sun here. It's the easiest one. And so you can remove them and then sketch where you're going to make your hole punches on your mask. So we're sketching each of our microchips. Next, what you're going to do is you're going to take your hole punch and you're going to punch holes wherever those circles were. All right. So that is one way to do the mask. The other way that, let me go back really quick to this. I just want to show you this. You can create the art with the 6 chips, or this is very real world, is every wafer can produce up to 300, 400 microchips. And the goal is to continue to get more microchips to make as much money as possible, right? So another challenge could be, instead of doing the art, you could totally skip the art if you don't like it or it's confusing. And you could just tell kids, maximize the number of chips that you can fit on your wafer. So then they might, maybe you contain it to up to 12 chips and see if they can fit all 12 on without shorting, all right? So that's another pathway, or you could have kids do both, right? Whatever you prefer. So, all right. So the next step, we're gonna go to the next step now. So we're gonna we're back into the fab, we're back into the lab in the clean room. We're gonna take the wafer that you've already put together, that you had the wafer, the cleaning and polish, and the deposition layer, and it's now ready for your mask. So let's go. So you're going to get your mask that you just made, and you're going to lay it on to your wafer. Now, this step is modeling photolithography. And we're going to lay it on the layer, modeling photolithography, and then we're going to etch away with tweezers the material, making room for conductive traces to be added later. We'll talk about that in a minute. But this etching is the process of removing unwanted material to create the features of the chip. I'm going to pause us for a minute. So this step is called etching, and it's the process of removing unwanted material to create the features of the chip by using chemicals that eat away at the wafer's exposed area, leaving behind the desired pattern. It also removes the underlying layers of silicone and other materials in the pattern of the circuit design. So this etching, you can see we use the tweezers to do this, and you just kind of stick the tweezers down into the holes that you hole punched and gently lift up some of the Play-Doh. All right, let's continue. All right, so the next step is you're going to take your mask off. That part is done. Now you're going to cut another plastic circle larger than your wafer out of that same sandwich bag. And this step, actually, we're going to layer it over where you just etched. And what you're going to do is you're going to take the end of one of your LEDs and you're going to gently stick it into each of those holes that you just etched away. And being sure to push the plastic down into that as best you can, and then flatten. It's kind of a little bit of a process. And you're going to think about this as the deposition step. Deposition involves adding a blanket of conducting and non-conducting material, depending on the desired properties of the final product. All right, so now so now you got that. Now what we're going to do is we're going to add the vias, the conductive material, or small Play-Doh tubes. We're getting our Play-Doh out, and we're going to add those right into those holes. These vias, you guys, are little wires that let us go from one layer of the microchip to another, almost like an elevator in the circuit, where we can go from one layer to another, via to via. All right, so we're going to take our time to get this in. This is where you got to be careful about shorting. You don't want those two conductive pieces of Play-Doh, the vias, to touch. All right, I'm going to pause. Okay, so you've got your vias now, right? That takes a little bit of time. The next step is doping. For each chip, we're going to insert each leg of the LED carefully into those two vias that you just made. And so what I want to explain is this doping process is the process of changing the properties of the silicone in the wafer to create different components of the chip. And this is done by introducing impurities into the silicone, which changes the conductivity. And the type and the amount of impurities depends on the silicone, depends on whether the silicone becomes a certain type. And they're called N types, which is excess electrons, or P types, which is a shortage of electrons. And these are made with machines called implanters, where the N and the P meet. P-junction, and this makes the basis for something called the transistor, which we were talking about. Transistors keeps coming up because it is actually a critical electronic component in microchips. It is the switch in the chip. The switching capability is actually essential for microchips. And so there's a whole great resource we have around transistors. All right, let's continue. We're almost there. Great. So you're going to add the LEDs, right? This is the doping. And that the LEDs sort of complete our microchips. So we have 1, 2, 3, 4, 5, 6, 7 microchips for ours. Great. Now, the final step. Well, sorry, there's one more step in between. Now that we've got our microchips, I want to note that the one step that we don't really talk about, we allude to, is that microchips are made out of many, many layers. They have many layers of connections and patterns, and the number of layers is actually a key part of the innovation of chips currently today and is often proprietary. If you do research, you'll find that some say, oh, it's 9 layers or 11 layers, but all the engineers on the edge of this technology are innovating on the number of layers and the chips and the complexity of what can happen. It's really exciting. All right, so we mentioned layers, and now the final piece is quality control, right? You heard in that video that quality control happens all along the way in the process. We're heavy hitting it right here, where we're going to actually test each of our chips. And so let's watch it. So when you test your chip, you're determining if the chip works for the amount of yield. For each chip, you're going to insert the battery pack to the positive and negative, and then see if it lights up. If it lights up, it's a yes, right? It means it worked. And the goal in real life is that every wafer would yield 100% of their microchips. All microchips would work. And so we've ensured success in this design challenge that every microchip, every one of those should work if the kids didn't put didn't short those circuits, right? So it's pretty easy for success there. Yeah, so that's the challenge. I want to go over, and I would like to ask, I don't know if anybody's doing it, but it would be great to know if you are doing it. How many successful chips did your design yield? Did you get 100% yield? That would be great to know. Awesome. All right. And so I want to close this part of the session, this hands-on piece, with this. Because this is a model, I want to be clear that we've taken lots of liberties with this model in order to make the concepts of semiconductors accessible to the pre-university, the school-age children, K-12, right? Working on this project, we actually learned that the concepts are so complicated that sometimes electrical engineering students don't begin to explore the concepts until their junior or senior year, and some graduate without designing a chip at all. So yeah, it's pretty interesting. I would love for you guys to, before we transition to our resources, it would be great to know if you were doing this with us, or just your reflections on this model. Would love to share any insights in the chat. I would love to see what your thoughts are. What's the mission and the purpose of the chip? That's a great question. I think that's something actually that would be great for you guys as when you're doing this with your students, to ask that, like, where do they want this chip to go, right? And that's a critical piece when you get down into the integrated circuit design and what's the function of the circuit and what's the goal of it. That's a really good point to not miss. That's right. All right. Thank you for asking that. Thank you for bringing that up, Richard. All right, well, with that, I'm going to go ahead and share our resources and where they can be found, and then we'll take some questions and along the way here. So all of these resources, Debbie already put it in the chat a while ago. They can be found on TryEngineering Semiconductor Collection, and the link is already in the chat. The resources include 3 videos featuring industry experts, which you saw the first one, and we'll talk about the other 2 in a bit, an ebook, and the hands-on activity, as well as these really cool missions that I'll talk about in a little bit. These are designed to give educators options. You can use one or all. You might decide that you just want to use a video or just the ebook, or maybe you love the interdisciplinary missions. So let us go into each of the resources in a little bit more depth before we jump out. So IEEE, that first video that you saw was professionally done, and we have 2 more like that dive deeper into the industry. We partnered with a company called Rubicon Industries to develop 3 5-minute videos. And the second video is the semiconductor industry video. This one is my favorite. It goes into the history of semiconductors and the careers in the semiconductor industry. It's really cool. And the next one is the electronic packaging. This goes behind the scenes at a research facility and a microchip packaging facility to learn about how these chips are made and packaged. And these are great resources to use with your students, like just 5 minutes and then a debriefing session. And you will literally have introduced your kids to the world of semiconductors. So videos are a great resource. The next resource is an ebook. This is called Microchip Adventures, A Journey into the World of Semiconductors. And it's designed in a fun and creative way. The goal of this was this interactive tool for educators to use with kids. And you could take pieces of it or all of it. It's a lot. It really focuses on introducing the language, the vocabulary of the semiconductor industry. It links to hands-on activities and videos throughout the ebook. And it features, the core of the ebook features this lesson that we just did with you, this hands-on activity that we did with you. And also, something that I'll talk to you about in a minute is it also features these student-centered missions that are interdisciplinary. So again, let me share that. So these resources are all free and available to you. The final resource is these 5 missions. They're dig deeper type missions. These are extension activities designed to take the concept of what we covered and launch your kids into a deeper, more active learning activity. These are cross-curricular, so you can use them in your social studies class, in your English class, in your math class. So for example, the materials mission is one of my favorites. It uses simulations to help students really grasp the difference between conductors and insulators. We also have one that gets into the P types and N types, which is very cool for older kids. The nanoscale mission challenges them to apply Moore's law and predict what's next in technology. This is great for math class because it focuses on nanoscale, which is very cool, and exponentials and growth. The real value here is flexibility with all of our resources. These are a la carte resources. You can select just, say, the history mission to spark a debate on the transistor's impact, or the supply chain mission, which is one of my favorites. It's a creative team story activity to learn about supply chain issues. They're all featured in the ebook and are linked to the hands-on activities, giving you multiple ways to engage students in these real-world relevant engineering and science activities. So I would love for you to take some time to explore them. We've been popping them over in the chat. And yeah, love to hear. We're going to be entertaining some questions. But before we do that, I want to close with this one final opportunity. We have these educator sessions that we started 2 years ago, I believe. 2 years ago, yes. And Debbie mentioned them. They were specifically on this particular lesson and our resources around semiconductors, but we're growing these. Our sessions are going to expand in content, and so we're super excited about that. You can see the format of these include industry experts, include a hands-on activity on various tech topics, and then also a tour, facilities through tours, looking at, we've been in research facilities, seeing their clean lab, that kind of thing. So, but what's so cool about this year, let me get to this, is that, as I mentioned, we're expanding the content. So not only will it be about semiconductors, but also AI and possibly other technical topics, where you get to hear again from industry experts and gain access to our resources. So participants that are selected to attend it's for free, you guys, and you get a stipend. How awesome is that? So we have 3 coming up this summer. We have one in Florida, one in Arizona, and one in Minnesota. No, Minneapolis. Yeah, Minnesota. Yeah. Minneapolis. So we're super excited. They are 2-day events, and they are a blast. There's nothing like it. Super fun and a great opportunity for you to meet other, educators who are like-minded and interested in, diving into the tech in a deeper way. So with that, I think we're going to entertain some questions.
So before we get to the questions, and thank you, Donna, for all of that. I hope everybody feels really inspired and excited about bringing this back to your classroom. And in order to help you bring this back to your classroom, TryEngineering has a classroom set of materials that includes everything that Donna shared with you today and enough to use with at least 30 students. So our only restriction is that you had to be here today and you have to be in a classroom. So you have to be a classroom teacher. We're only permitted to send it to a school. So if you work at a school and would like to be considered for this, please type in the name of your school. And in a few minutes, as we finish up the questions, we will pick our winner for this. So right now, if you teach in a school, please type in the name of your school. That will give us your name and school. And if you are the selected winner, we'll get all your other information. So go ahead, you could type it into the chat right now if you work in a school. Thank you. Hope more than one person, we think. And while people are typing this in, I won't answer, well, maybe I can start answering some questions. If you have some questions, please use the Q&A feature at the bottom of your screen. And we have a few more minutes for any questions related to the lesson that you just saw or TryEngineering overall, or my colleagues at Kaptivate, I'm sure will jump right in for Kaptivate answers as well.
Great. What a wonderful presentation. Thank you both so much. We are going to move into the Q&A section. Hi, everyone. I'm Quinn. I work at Kaptivate. If you do have to hop off at all, then please feel free to fill out the survey that's going to be dropped in the chat right now. We know sometimes people have to go on the half hours and the hours. So thank you for your attention during that time. There was a question in the chat that, I think, as things were going on, people get, excited. And this one question said, how can I integrate these educational pieces into my physical computing classes? That's kind of a cool question. I don't know if you have any thoughts on how we can take these hands-on learning like this into physical computing classes.
Yeah, actually, Quinn, thank you for that question. And we designed this question with a target audience of middle schoolers. And the reason why we have that as a target audience is because we know that there are going to be elementary schools that can incorporate pieces. And we were hoping that there were some high schools, maybe with very limited introduction to electronics, that might be able to incorporate some of these pieces. And what we found out is the most engaged teachers that we had were teachers that were doing some higher level physical computing or coding because they felt that their students were doing really well in that, but didn't really understand the model that was making all this work. And so one of our AP computer science teachers brought this right into our classroom and invited one of our volunteers to speak to our students in order to be able to understand a little bit more about, I'll call it the magic of the microchip and the work that people have done over the last 50 years to shrink the microchip, which is what allows us now to walk around with phones all the time. And 50 years ago, all we had, or 40 years ago, was access to a computer. So that would be my best explanation in answer to that question. We do still have some other lessons that talk a bit more about physical computing, but that's what we had heard from our teachers.
Wonderful. Great. Great. Valerie had a question. Valerie, do you want to come off mute if you can to ask your question so you can clarify? You were asked about go ahead.
Your summer workshop that you have in Minneapolis and Arizona that you just showed on your last slide. Can you tell us about the professors, facilitators, educators who are helping to make that possible for those 2 days?
Yeah, so we do this with a team, Valerie, of educators who've been in the classroom, along with professors that are on site that are doing research in the area, and IEEE volunteers that are local. Each of the schools that we've chosen have semiconductor facilities there, and that's why we started there. So some of them have staff that only do this, but we use our resources here at IEEE and bring in some of the experts. Sometimes we have to tell people no because we have so many people that want to talk to the teachers and we just want to do the work. But it's a combination of high school teacher. In the last couple of years, that's been Donna and me, and we're looking at expanding our semiconductor experts at those facilities, which are sometimes from industry and sometimes from the sites themselves, and IEEE members serving as professors in those locations.
Great, thank you.
Mhm.
Bobby has a question. Do you want to come off mute if you can, Bobby, to ask your question?
Sure. So my question is, how do you balance the conversation when it comes to ESG concerns? It strikes me that Gen Z is very savvy about, ethical concerns, environmental concerns, and also understanding how all of this boom is going to impact the price of things and the cost of living for them. And so, it's fun to do the exploration piece, but then there's the reality of the work. And I'm just curious how you balance that conversation when you have both their curiosity of learning the engineering side of things, but also wanting to be well versed or understanding to some of those other concerns.
Thank you so much for that question, Bobby. And that is a question that we love here at IEEE, particularly in this particular area and artificial intelligence. One of the environmental concerns with artificial intelligence is the data centers that are going to need to be built in order to sustain what we anticipate is going to come. And so my words to both the teachers and the students that I work with is that's exactly why we need you. How can we do this faster? How can we do this better? How can we do this smaller? And if people never started working on the microchip, we would still have chips and resources that are more expensive and bigger and never have the kinds of solutions that we have now. And so it takes a lot of creative and diverse thinkers in order to come up with these solutions. I don't necessarily know what they are right now, but ethics, conservation of energy, ability to bring things to market in a way that everyone can have access to the technology is something that we're very concerned about. And this is why we want everyone to learn about this. I hope that helps.
Great. We had another question in the Q&A. Juan is wondering if IEEE has ever had any interest in organizing a semiconductor teacher workshop in Europe.
Well, that's very interesting because we have IEEE volunteers that are very involved in Europe and in fact just hosted a session in Greece where it was a student session. And so we trained the teachers right before the student session so that they could deliver it. We are always interested in doing something like that. It just takes resources. And so we need the right university, the right IEEE members, and we'd certainly be able to do it. It is our goal for all children to be exposed to engineering in every part of the world.
That's wonderful. We had another question, which actually I was interested in knowing too, having worked in classrooms. Does TryEngineering offer grants for supplies for these types of lessons, or I'm going to add on, have you seen creative ways that people and classroom teachers have been able to secure those kinds of supplies?
So yes, so a couple things. Annually, we have a STEM grant, and last year we awarded $70,000 to IEEE members who wanted to put things like this into their after school clubs or in collaboration with the teachers. We also have a STEM grant for teachers going on right now, but it's not for this. It's for service learning, but you will see that on our website in the next day or two, and we'll send you information about that. But you will find that it's TryEngineering's goal to have low-cost materials. So the materials that we use today are surprisingly inexpensive. They're not accessible everywhere. no, we found no Play-Doh in Greece. We had to use something else. But there are materials everywhere, and they are surprisingly inexpensive. So if you have a small budget, I would recommend using that budget. I also know here in the US, we have very involved parent communities who would love if you just put a material list together. And in fact, we can do that for you. We can put the material list together for you and show you that a classroom set costs about $250. And you may have a PTA or a very involved parent that would be interested in bringing this to your classroom.
I've seen teachers use things like wish lists on Amazon and put those up on their own social medias and different communities. So another great
Yes.
way to get the community involved and excited. And
Yeah,
also,
thank you for that.
I would just say from personal experience, like local companies or civic organizations like Rotary clubs, Kiwanis clubs, those kinds of places often will have small grants that people can apply for that they don't even know about that they could enrich a classroom with. Great. Any other questions? Those were all the ones that were in the Q&A. But if folks have any others, you're welcome to drop them in there. And if not, you do have their email address here. Let's see. I'm gonna just look and see if there's any that got in the chat. My mistake. Okay, great. Wonderful. Okay, well, that might just be all of our Q&A. So I am going to put up my slides again for a couple more announcements for everyone.
Oh, sorry.
Oh, no worries.
So Quinn, yeah, Dawn has access to it. You don't.
Oh, okay, great.
So does Phil. I put the winner in the.
Oh, the winner. Okay, you want to announce it?
Oh, where is it?
Jack Crowder, you win.
Yay.
Yay, and a middle school. Thank you so much. So we're happy about that. We'll reach out to you for your actual shipping information. Thank you so much.
That's wonderful.
Wonderful.
Great. All right. All right, a couple other announcements before we go. All right, well, I just want to give a huge thank you to Debbie and Donna for this incredible hands-on workshop. It's so fun. I just feel like for an afternoon, for some of us, wherever we are in the country or in the world, it's nice to have like an afternoon pick-me-up like this to be able to have like a fun activity to do in the afternoon. So I just really appreciate what you've presented and just what an incredible resource IEEE TryEngineering is. I've checked out that website and I'm just very impressed. I've been sharing it on LinkedIn with friends just because I know a lot of teachers out there that are looking for good hands-on activities to do. Just a reminder too to join the TalentSHIFT Advanced Manufacturing Collaborative. So working with wonderful organizations like IEEE TryEngineering, we put on workshops like this, hands-on learning. But it's also, there's an online collaboration space where you can meet like-minded people like you who are in the same field, share resources, and just learn more. We have meetup times online if you just need somebody to talk to and bounce ideas off of, we do that. And then, of course, we have events just like this. So please sign up for membership on there. And we also have a QR code here. We have a lot of QR codes today. So get your phones out. You can sign up for the TryEngineering newsletter, continue to find out about great resources that they're sharing on their website. So we just really hope that you learned something new and that we really look forward to seeing you at our next event. So just please take this post-event survey and leave your feedback for us. This helps us improve what we're doing and make our future events more exciting, more popular. So please share this with others who weren't able to make it today. And we just thank you for your attention and for being here. And one more round of applause to our wonderful presenters. Thank you all so much.